This is Humans.
Humans. I'm
Hank Green. The amount of stuff that we know is a little bit devastating. It's easy to forget that it wasn't long ago that we had every reason to believe that the Earth was the center of the universe, and the center of the Earth was the human, and people were the entire reason for things to exist. And that's entirely logical, given the data we had back then. And of course, there are lots of people who still believe that, but there are fewer reasons to believe it than there used to be. About 100 years ago, we figured out that there were other galaxies, which just seems so recent to me. And since then, we found out a bunch of other absolutely nutty things about the universe. That it had a beginning, that there are kinds of stars that can exist in the universe and they change over time, that matter and energy are the same thing, that space and time are the same thing, that we can see the beginning of the universe, and that we are kind of at the beginning of things, and in another way that nobody ever talks about, upsettingly close to the end. Katie Mack is a cosmologist, the kind of person who studies the cosmos, the universe, everything, and how everything relates to everything else, which is the thing that, in my worldview, somehow gave rise to country and Western music. I have so many things I want to talk with Katie about all of the time, and so I'm very happy I get to talk with her today about light years and dark matter and what it feels like to realize you live inside of something this weird, about why we went back to the moon and why that was somehow really nice, and about how we figure things out and how we share them with other people. Katie Mack, human cosmologist, welcome to Humans.
Thank you. Thank you very much for having me.
In the Big Bang Theory, Sheldon and Leonard live in the same building as Penny, who is a waitress, and the internet asks, does anybody think that it's weird that Penny, a waitress, is able to afford rent in a building where two PhD physicists had to be roommates and split rent?
No, that's not surprising at all.
It's not weird at all. It would seem like these two PhD physicists who know everything about the universe should be being paid well.
You would think, and yet. It's very, very common for postdoctoral researchers, which I think these guys are, to have housemates, to live very cheaply. Once you're a postdoc, you're probably above the poverty line, but that's the first time in your academic career when you're above the poverty line generally.
You maybe have a lot of debt that you need to start paying off.
Yeah. Academia is not a lucrative business for most people.
This is super interesting to me. So of course there are ways that you might go from academia into an industry where you do make money.
Yeah.
There's lots of big math nerds in finance that make a lot of
absolutely,
money.
Yeah.
Modeling can be very useful for understanding the universe, but also useful for understanding all kinds of valuable things that people will pay you for. Mm-hmm. But if you're going to stick around in academia and actually discover things, it's very much a passion thing.
Yeah. So my first faculty job was at North Carolina State, and I took couple of months off between my postdoc position and my faculty job. And so when I got to NC State, at some point I realized that if I was going to pay my first month's rent, I had to get a credit card with one of those, you don't have to pay it off for a year things to get a couch. You do not, once you're a professor, then it starts to be comfortable. But before that, it's just not.
Yeah, it starts to be comfortable, but also you're working up to the comfort. Yeah. And there's also lots of different kinds of professors. Now many people who teach students are adjuncts.
The adjunct thing, that can be there are a lot of people who are adjunct faculty who are on food stamps and stuff. If you're in a full-time tenure track job, then you can be doing well, but it's tough, yeah.
There's celebrity professors who make tons and tons and tons of money, which is also a weird thing.
They don't necessarily make it from the university. They make it from speaking and books and that kind of thing.
So, science requires money largely because it requires scientists, but also because sometimes it requires extraordinarily expensive experiments. Mm-hmm. We have to decide to do it.
Yeah.
And when I think back to a lot of I know a lot about Antoine Lavoisier because I'm a chemist and I love that guy. And he was only able to fund his work because he was rich. Mm-hmm. This was how it used to be done. Rich guys would be bored, and in between tax collecting, which is why Antoine Lavoisier ended up getting killed in the revolution, he would do very important science. And now we sort of decide largely to fund this collectively through a very sort of cobbled together system that was not necessarily intentionally made this way, but it's largely based around universities, right?
There are some places like the Perimeter Institute where I work, which is a non-university research institute, but even that is, I think about 2/3 of the funding is government funding at some level. It was founded by philanthropy, but then we get grants from the government to carry out our work. And I have a grant from the Canadian government in order to supervise PhD students. If I didn't have that grant, I couldn't be a PhD supervisor. So it is still very, very much government funded.
So this is a thing that we're all kind of deciding to do together.
Yeah.
Which is strange because, of course, like what the government does is, to what extent do we decide it? And I've been thinking, you and I had an interaction on Blue Sky where you were talking about Artemis.
Yeah.
Can you give me your Artemis take?
Yeah, so I found the whole mission joyful.
Oh, yeah.
It was so much fun to watch and to just follow where they were at, to see the interactions of the astronauts themselves, to listen in on their conversations with mission control and, what they were seeing, to follow all the weird little problems like the fact that the toilet got stuck and they couldn't take the toilet fixed and
4 roommates in a small studio apartment with a broken toilet.
The images were incredible, and seeing the images of the Earth from space and the moon and the Earth and the moon together and the eclipse, and there was so many joyful things about it, and it was so much fun to watch as just a demonstration of what humans can do working together in collaborations of competent and excited and passionate people.
Yeah, competent is such an interesting thing there. I kept thinking about that, where it's like, oh my gosh, look, it's people good at their jobs.
Yeah.
They're so good at their jobs.
Yeah. They're good at their jobs and they genuinely care about what they do to an extreme degree, in a way that is inspiring. I loved watching it. There was some cool science aspects about, what they're learning about the moon and about meteorite impacts and so on. But there was also a lot of commentary about, like, is this a good use of public funding? And is this really just about the military industrial complex? And is it just national posturing? And are we going to do mining of the moon for resource extraction? And like, is that the purpose of this whole thing?
Yeah.
And there were a lot of really, really smart comments, a lot of really thoughtful discussions. But there were also a lot of claims where like people were saying like, this is a waste of money because it's not the most efficient way to get the science, because you could send a robot, you could get more science for less with a robot. And I felt like that was a little bit of an unfair criticism of Artemis specifically because that wasn't the choice that was on the table, right?
Right.
The administration wanted to send people to the moon for their own reasons, which we may or may not like, but they want to send people to the moon and they want to build a moon base.
Yeah.
And so the engineers and the scientists were like, we're going to make this happen. And they made it happen. And they found a way to add some science to the mission. They're not just flying around. They're taking data. They're talking to the geologists. They're doing a ton of experiments on the humans on the way. All of this science is kind of built into the mission. And it's stuff that just wouldn't have happened. There isn't a robotic mission that was canceled for the purpose of Artemis. There is science being canceled, but it's not because of Artemis. It has nothing to do with the moon mission.
I think that science should be like more salient. I think it should be easier to pay attention to. I think it should be pitched in such a way that is like there are on-ramps for people. And if those on-ramps are expensive, then that's actually valuable. The idea that science exists and should only be for PhDs is really wrong to me. We are a humanity, and so we should all be invited into this thing.
Yeah.
And you replied saying that Artemis is like a cathedral in a way.
Yeah, so I was thinking about this when it was launching. Like, when we build rockets, it's similar to why we build cathedrals. It's this idea that we are creating something big and expensive and powerful for the future, reaching something that we can't otherwise reach. Like, it's an investment in the future. It's a big collective thing that not everybody who works on it is going to see the benefit of. But it's something that we do because we have this sense of awe and we want to touch something, higher than ourselves.
Reaching something that we couldn't otherwise reach. Like, that is what cathedrals are about.
Yeah.
It's like, let's build this thing. And when you're inside of it, I mean, as a secular guy, like inside of a cathedral, you still feel it, right?
Yeah, absolutely.
And in the same way, like we all gather in a cathedral, and that's what the purpose is also, is to be a space in which people gather. And like, a live stream is a weird place for people to gather, but we were,
Yeah, absolutely.
We're all having that experience together. We were all like very Super Bowl, but for nerds kind of feeling.
Yeah.
And, the Super Bowl's expensive. And a lot of money gets spent on it. I actually don't know how you would line up Super Bowls versus Artemis. There might be an extra zero on Artemis. There's a way in which I would hate it, which is if like they put a bunch of broy podcasters on the in the capsule and they were all like Trump the whole time,
Yeah, of course.
But that's not what happened. It was a bunch of people who were just grateful and connected and competent and kind and moments poetic.
Yeah, absolutely.
I think that we need these places to gather, and I think that we need ways to reach something that's beyond our reach, and that is what it felt like.
Yeah, and I think that that's one of the arguments for human spaceflight as, we could have sent a robot, we could have sent really intelligent robots that could do observations, respond very quickly, but there is a value for humans to see humans experiencing a thing and for us to feel like we are part of that. We say we went to the moon, right? Like that is how we put it. It's a collective endeavor, even though very small number of people have been to the moon or even to the vicinity of the moon. But it's something that we feel as people.
Yeah.
And I think that that's very valuable as a thing that's just enriching of human life, but also as inspiration, the way that people connect with science through that. I do think there's value to it. I think human spaceflight is important, and not because it's the most scientifically efficient thing to do.
Yeah, I just think a lot about these on-ramps into science and caring and learning, and nothing is as universally salient as like a solid rocket booster. Just absolutely smashing 4 people into their seats as they accelerate to, Mach 37 or whatever. I just think it's awesome. So I want to ask you another question about the actual Big Bang Theory. You have a great poetic line that sticks with me. So because light has a speed and it travels from very far away, that light that we're seeing from very far away is from a long, long time ago. And if we look far enough away, you have used the phrase that we can see a world that is still on fire from the heat of creation.
Yeah.
What do you mean?
So let me just first start with the definition of the Big Bang Theory as a cosmologist uses the term. Because there are lots of ways people think about the Big Bang. Sometimes people think about the Big Bang as like a singularity, which is a whole other kind of topic, really. But when a cosmologist says the Big Bang Theory specifically, what we're usually talking about is the idea that the universe in its early times was hot and dense and in some sense smaller than it is today. And you just get that. What?
I like that you qualify smaller with in some sense.
Well,
because it was infinite then, but it was a much smaller infinite.
Right. This is the problem. Like maybe it was infinite, maybe not. Like we don't, but there's a scale to the universe, and that scale is bigger now than it was at the time. And we just get there by saying we see that the universe is currently expanding. Therefore, in the past, it was less expanded. So if you take the Big Bang Theory and you say that the universe was hotter and denser in the distant past, and then you take the fact that we can see the past by looking at the distance, which is just wild to me, but it's true. If you look at something far enough away, you're looking far in the past. It's wild because people think about it in terms of like, oh yeah, the stars, that's like 20 years ago is that star was shining, whatever. But it's like true in this room, right? Like if I look at something that's a foot away, it's a nanosecond in the past to me. And like, that's just always the case. Everything you see is in the past. But yeah, so if you look farther and farther away, you're looking farther in the past. And so in principle, then it means that you can see so far in the past that you're seeing the beginning of the universe, the time when the universe was hot and dense. And so you would imagine you should be able to see that fire, right? Like if the whole universe was fire because everything was hot and dense and glowing with heat, then you should see that fire. And you would imagine that means that the sky should be bright, right? Because you'd look out and you'd see this fire all around you. But in a sense, it is because that light is there. And so we can directly see the parts of the universe that are still on fire from our perspective, and they are the farthest reaches in any direction you look. And so we see that fire, and it's just we see it in microwave radiation because the light's been stretched out, but it's there.
And so it's been stretched out by literally the stretching of space.
Yeah, the expansion of the universe. Yeah.
So that the waves are in a kind of property of space-time, and that space-time is stretching.
The waves are not a property of space-time, but they're moving through a stretching space, and that kind of stretches out their wavelengths. You can think about it as like things are moving away from us, and there's a Doppler shift of light.
Yeah.
But then that gets tricky because the expansion rate would be more than the speed of light. If you expand something just universally, like you say, over the course of a certain amount of time, it doubles in size, then things that were very close together are a little bit farther apart, but things that were already far apart are a lot farther apart.
Yeah.
And if you have a big enough universe, you always get to a point where the separation between two things that are far enough apart is faster than the speed of light. But they're not moving, so it's okay. Right? Like they're just the space is moving.
It's not breaking the rule.
Yeah.
It's not breaking the speed of light.
It's not breaking the rules.
Is it okay, though? I don't know about
okay.
that.
That's a separate question, perhaps. Yeah.
So another thing that this causes me to wonder is, at what point did the light get shifted into the non-visible part of the spectrum, or at what point was it still in the visible part of the spectrum?
Yeah.
Like if we existed in an earlier universe, we could see the Big Bang with our eyes.
Yeah, so you'd have to be pretty early on for it to be visible light.
But there was a time, not soon enough, that like there was carbon, probably.
Right. Yeah.
Okay.
Yeah. No, way before there was carbon. Yeah.
Oh, well,
Yeah.
that's too
So-
bad. We couldn't have existed then. So did it even exist? But it did. And so we could imagine it. And we could imagine being maybe on a planet. Maybe there wasn't
Sure.
stuff for planets to be made of. Maybe a
Right.
gas giant. And we would be able to see the Big Bang everywhere all around us. And in the same way, we're sort of like in a middle spot now where we can look up at the sky and see stuff. But someday in the future, a long, long time from now, there will be a sky with no stuff.
And it's not even that, well, okay.
It's not even that long from now,
So the time frames get complicated, right? Because I think about super long times in the future because I think about the end of the universe professionally. And in the next billion years or so, the sun is going to destroy the earth. That's like a short time frame from now, like in terms of.
It's a short time frame in terms of life. Like life has been around for 4 billion years, and so that's like just another one.
Yeah.
We're on the tail end of a livable Earth. No one talks about this.
Yeah. The habitability of the Earth is a temporary thing. The universe has been around for about 13.8 billion years. Our solar system about 5 billion years, something like that. And in about 1 billion years, the sun will be so bright that it'll boil the oceans.
Yeah.
And the Earth is effectively dead at that point.
Microbes might hang around under the surface for a while,
Sure.
but like that's not what we care about.
But then if you go farther into the future, like, about 5 billion years, the sun is going to puff up and be a red giant and turn into a white dwarf. And then in about 100 billion years, we'll be at a point where we will not be able to see other galaxies anymore.
I mean, we can barely see other galaxies now
We can see some of the nearby ones.
with my eyes.
Well, by eye, you can see some of the nearby ones. You can see the Andromeda galaxy. You can see the Large and Small Magellanic Clouds. Those are all going to merge with us before that happens. But then there are other galaxies where even if you put like Hubble Space Telescope up in 100 billion years,
The light would not be able to reach us.
yeah, it wouldn't be able to reach us. So
At what point can we not see stars anymore? Does that exist?
Yeah, the stars will burn out. The red ones last a while, so red dwarfs can last billions of years.
Oh, I guess the big thing would not be that the stars get farther away. It's simply
No,
that
we'll
they-
have more stars actually because we're going to have other galaxies merging with us.
So the universe is going to keep happening. Like there's nothing that's going to stop the universe from happening. But there is a way in which we are kind of at the end of the beginning here.
When I learned this, it kind of freaked me out. So we know that stars form when gas clouds come together and get really dense and ignite and so on. And one of the ways that happens is by galaxies colliding and mixing the gas up, or galaxies using the gas that's already in them. We know that there was a time in the past in the universe 5 or 6 billion years ago when there were way more galaxy collisions. The stars were forming much faster. There was a lot more star formation. And we can trace how that star formation rate has been going down. And we can look into the future in terms of like extrapolating the current expansion and see how that star formation rate is going to go down even more. And what we can find when we do that is that of all the stars that have ever formed or ever will form, about 90 or 95% of them have already happened. And so from now until the end of time, it's like we're working on the last 5 or 10% of creation.
We're going to have to put a disclaimer on this episode. Up front, before the intro, I'm going to have to be like, look, you guys.
Yeah.
Let's be
Yeah.
careful with this one. I think often about the 4 billion years of unbroken life. So just like the same system of living chemistry happening for 4 billion years on a planet that's relatively stable around a star that is relatively stable.
Yeah.
I wonder if, I don't know, if we should talk about the Fermi paradox, which is the idea that it seems awfully odd that if things tend to use up the resources available to them
Right.
and then hit a carrying capacity, which is what living things tend to do, though maybe not what intelligent things do, then why hasn't something come around before us and used up all of the resources in the Milky Way? And it definitely hasn't happened. And one potential is just that like it takes a long time to go from a cell to country and Western music and like Artemis, you know?
Yeah.
And maybe it's just really weird for that level of stability to last for that long. And it did take us until the end of the sort of livable
Yeah.
time of the Earth, roughly, 4/5 of the way through.
I feel like the Fermi paradox, like there are a lot of assumptions that are built into that.
Yeah.
Like the idea that it's inevitable that life will want to expand beyond its planet or try and talk to other planets. I don't know how inevitable that is. I know that like we humans want to explore and expand and reach out, but I don't know to what extent that is a human thing.
I mean, I can hit you with a biology thing here,
Okay.
which is that like the thing that evolution selects for is making more of yourself. Like that's the only thing evolution selects for. If you can't do that, then there aren't more of you. And then somebody who can make more of themselves, they're the ones who take over the population. And, when I say they, I don't mean humans, I mean cells or crows or something. But it might be very different on the scale of like things that can traverse the stars. They might not want that. Indeed, we're seeing right now that like humans don't create infinite humans when given infinite resources. Eventually we're like, actually, that sounds hard. Maybe not. And I don't know what that means, but it is like an assumption that I would say like, oh, greater than 50% chance that like, whatever things make more of themselves, there are more of them. And so that's the thing that evolution is selecting for. But like, maybe not. Maybe when you get intelligent enough to go to the stars, you're also like, that level of ambition is beyond me. And I think that there should be a finite number of us living happy lives.
Yeah. I mean, it's entirely possible. Like there's just a lot we don't know about what other life or other intelligence might do or want or what kind of constraints you might run into if you start to try those things, right? Like we have this idea that it should be possible to make generation ships and so on, but there are reasons why that just might never work, that we might never be able to survive on something that is not the Earth. That's possible. So
yeah, I think we could probably solve that problem.
I think probably, but there have been compelling arguments that like, maybe not. I've read some really fun science fiction stories about that go through all the things that go wrong if you try and live in a generation system.
Aurora.
Yeah, Aurora. That's my favorite.
Yeah. There's a Kim Stanley Robinson book that's about that. Yeah. It's so good.
Yeah.
It's so
good.
It's so messy and human. And I love an insane artificial intelligence. That's one of my favorite tropes. An AI that goes crazy. I'm like, yeah, that seems like it would happen.
Yeah. No, Aurora was one of those books that like I always tell people like, please go read this and then talk to me about it because it's so good.
So we've covered a lot of weird ground already. You spend a lot of time thinking about dark matter, if I'm not wrong.
Yes.
So what dark matter is it's something that explains a thing that doesn't make sense. A lot of times people think of dark matter as like, okay, so there's matter out there and it's dark. It's probably that, but we don't even know that. What we have is a problem and we're looking for a solution. And the thing that solves the problem is matter that does not interact with the electromagnetic spectrum, which means that it doesn't touch stuff. You would think that it just means it doesn't make light, but it also like can't
It doesn't touch stuff.
bump into each other or like clomb together. First of all, this is very strange. The ability to like glow and the ability to touch are the same ability.
Yeah. So, okay, I will say, I think that dark matter's reputation as being a weird thing is a little unearned.
Okay.
So people talk about dark matter as though like, oh, there's this big mystery. We don't understand. We make this thing up. We don't know if it's real. that is all of physics. Like we see some data, there's some observation, it doesn't fit with our model, so we change the model, and then it fits with our model, and then we're like, okay, maybe we've discovered the thing. Like that is how the theory building works, right? Like, and it's always that way. And that's how we discovered, electrons and neutrons and
But there are other ideas that like don't require matter.
Sure, but they don't work as well. They just don't work as well. And there's nothing like there's this really fascinating phenomenon to me, which is that I feel like people are way more offended by the idea that we're proposing a new particle that has not been directly detected than the idea that we would propose to tweak the theory.
Right.
And I think that people think theories aren't real and particles are. It's almost the opposite. Right?
It's interesting. I feel like I've stepped in something that I did not know existed. Like this happens all the time. This is like the life of an internet person. It feels like I've wandered across a pile of dog shit that I did not know was there and I put my foot in it. There's a thing here that you feel you're defending, which is like, stop thinking that just because of a model like just change the nature of the universe rather than introduce some whole new thing. But like introducing some whole new thing is how we got neutrons. And it turns out that neutrons exist.
Yeah. And I think that like exactly what particles exist and exactly what their properties are is like not the most important part of the theories of fundamental physics that we have. Like the important parts of the theories of fundamental physics are like how interactions work, what kind of symmetries are involved, mathematical symmetries, the structure of the theory. And those are the things that are really sort of salient to the mathematical models we have of the universe. And then, the particles, the specific particles that are detected or not have to do with like what we can measure. And those measurements are always super indirect. Like when people talk about the discovery of the Higgs boson, nobody's ever seen a Higgs boson. Like we didn't catch one in a bottle. There was a model that suggested that a Higgs boson could decay into certain decay products. And then we looked at the data from the detectors that suggested that maybe those decay products existed very briefly and then turned into something else. And the rates are consistent with what we would expect for a Higgs boson decay. Like it's very...
And then you're like, we did it. It's there. There it is.
Right. And that's very indirect. And then people say, well, like, oh, you haven't detected the dark matter particle. Like, we have less reason to believe that we would because you can't catch it.
Yeah, the properties that we have assigned to this thing, the things that make it make sense are also the things that make it undetectable.
Exactly. Like, and there are possibilities for interactions that it might have where we would have an interaction in a detector.
Yeah.
And so we look for that in a bunch of different ways. But yeah, as you say, you can't touch it because like the way that things interact with light and the way they interact with each other are very related to electromagnetism and electrons and things like that.
We should say, though, why we think that they exist, which is basically galaxies don't work right. That's not how they should go.
It's not just galaxies, but yeah. So one thing is that galaxies seem to rotate too fast, and the stars toward the outer edges of the galaxies seem to be moving around too quickly, which suggests that there's more gravity holding them in. And the way that makes the most sense with the observations is that there's just more stuff. It's like 85% of the universe's mass is this dark matter.
You say that's not weird, but that's pretty weird.
I mean, yeah, and there are other particles we know of that also have mass but don't interact with light, like neutrinos, right? So neutrinos, there's a way that we can detect them indirectly, but they have very similar properties to what we think the dark matter has.
Yeah.
And we know that they exist. So it wouldn't be the only kind of particle that has this property. But yeah, we see the evidence in galaxy rotation. We see it in how galaxy clusters work. We see it in the structure of matter on very large scales, how galaxies and clusters come together. We see it in the patterns in the cosmic microwave background light, this background light from the Big Bang that like tells us something about what the universe was made of then and how matter was clustering then. There are a whole bunch of different things.
When you run the models with massive particles that do not interact electromagnetically, it explains a lot of this stuff.
It works, and for each of those different kinds of observations, you get the same kinds of particles and the same abundance and the same behaviors. And so it's like, it's circumstantial evidence in the sense that like we don't see the particle, but we couldn't see the particle. That's the whole point of that particle is that you can't see it.
The way that you get to communicate physics and the way that I get to communicate physics are necessarily going to be quite different. But it's still like my job to try and be an on-ramp for people into it.
Sure.
So I have to like start with what I definitely know, which is that something doesn't make sense. And so that's where I start. Something doesn't make sense. And then from there, I feel like what I'm hearing from you, and maybe I would hear something different if I was talking to a different physicist, but what I'm hearing from you is it's really almost definitely that there are actually particles here, that there's stuff that exists.
Yeah.
And it's a lot of the stuff. Is it possible that it's more than one stuff?
Yeah, absolutely. It's entirely possible that, okay, so it's this idea that, like, is it more extravagant to hypothesize one particle that we can't detect or a whole class of particles that we can't detect? I don't know. There's an argument against it being a lot of different things, only in the sense that if they interacted within themselves a whole lot, then they would start to act more like regular matter in the sense that they would like create equivalents of stars and planets and galaxy disks, and we know that they don't do that.
That's too bad we know that they don't do that, because it would be really cool if it turned out there was a dark universe.
Yeah, I mean, there are some models where you can get a bit of that, and there are some models where dark matter might be made of little black holes.
That actually appeals to me, because then it's not a new particle.
It's not a new particle, but you have to do really weird new physics in the early universe to make them happen.
Right, the idea being that in the early universe, a bunch of tiny black holes formed, and they're just flowing around all the time.
Yeah.
Like they're around us all right now.
Yeah, and I've written some papers about primordial black holes as dark matter. There are ways to make them work. Dark matter could be made of little black holes. It could be made of different kinds of particles. It could be made of some particles that sometimes interact a little bit and sometimes don't. It could be made of particles that when they interact with each other, they annihilate and create particles we can see, which we hope that happens sometimes, because then we would be able to learn more about them. There's a whole range of possibilities for what dark matter is. And
all this stuff is just getting figured out by people who have 5 roommates and their advisors.
Yeah, that's a lot of how this works. You know, people who are just, we really want to know what dark matter is, and so we're willing to like ignore the emails from the hedge funds telling us we can get 6-figure salaries and live in New York City, and instead we're going to live in a university town and eat ramen.
People don't like dark matter, but they don't mind the Big Bang. And this is weird to me, because there is no indication that the universe has a beginning in my personal experience, and it doesn't make sense that it does. It feels like something that should have always been here and will always be here. It will always be here, but it wasn't always here, which is very weird. You shrug as if it is in fact not weird.
Well, it's not that I think it's not weird. Whether or not it will always be here is also a question.
Yeah, okay. Okay. Well, that seems like the most likely thing to me.
There are different ways the universe could end, and
time will continue on. No?
So time will continue on, but in certain ways of thinking about the end of the universe, it will stop having a meaning the way it has a meaning now.
I should say here, Katie Mack has written a book called The End of, what is it called? The End of Everything Astrophysically Speaking?
Yeah, the end of everything astrophysically speaking.
And so Katie is used to talking about how it will all end.
Yes.
But time doesn't maybe keep going?
Well, so if you have the heat death, which is what we think is sort of the most likely end of the universe, which is where the universe just keeps expanding and expanding and cooling and gets more and more diffuse, then the end of the universe is when everything basically stops happening. Everything is spread out so much, everything is decayed into disorder. The second law of thermodynamics is this idea that disorder, or what we call entropy, increases into the future. And so if you leave something alone long enough, it falls apart. That's just how things happen in physics. And the universe will eventually sort of decay. So the entropy of the universe is always going up. But there's a point you can reach in this scenario where the entropy is at its maximum, where it just cannot decay anymore. It can't get any more disordered. And that's called the heat death of the universe. And the thing about time there is that the second law of thermodynamics says that entropy increases into the future. So if you don't have any way the entropy can increase, you kind of don't have a future. So time can pass, but it doesn't have an arrow anymore, which is a weird idea.
I've heard this before. It's very hard for me to accept that time is entropy dependent. They seem like pretty separate things.
I mean, it's not that time is, it's that the arrow of time is. It's that the way that we think about the difference between the past and the future is entropy dependent. Because most of physics doesn't care about past and future. Most things are kind of symmetric if you go back and forth, either direction. But entropy is like the main thing that where it's like you can really tell that there's a difference between the past and the future.
So if you just look at the solar system, like you run the solar system in reverse, it's just doing gravity. It's just doing momentum and
Yeah, like an orbit.
But with entropy, that is not the case. Like if you look at Jupiter, it's like more mixed up now than it used to be.
Sure, yeah. The particles are like diffusing into the universe.
And that's just been the whole time from the beginning. And so hot, dense, but also very ordered in the very beginning.
This is one of the big mysteries, actually, is like
your eyes just did an interesting thing.
Yeah. So
you got excited about that.
Yeah. This is one of the big questions is like, why was the universe, how was it in a low entropy state in the beginning? Like what set that up? That's an initial condition problem. Like the idea of the Big Bang is like, we don't have a good explanation for how the universe got to the point where it was low enough entropy that it could have been increasing all this time and, be at the state it's at now. So that's a big question. And people come up with new theories about the beginning of the universe to try to explain that. We don't have a good explanation for that at the moment.
I don't know if this is going to sound like it doesn't make any sense, but does that mean that like there is a way in which we are still on fire from the heat of creation? Or at least like warm?
In what sense? Like, what do you mean?
The sun is to some extent powered by the order that we started with.
I see what you're saying. I never thought about it that way. I don't know. I wouldn't call that on fire, but
warmed.
Yeah, I mean, we're still basking in the cosmic microwave background, which is the fire, right? That is that fire, and we're just far away from it now.
Yeah, but we're also kind of like basking in the order of the starting conditions of the universe.
Sure, yeah. Like the way the universe is now is the way it is because of how it started.
But like the order that we have now is kind of that order, just decayed.
Oh, I see. Yeah, I'd have to think about that, but I think you could say that. Like we're still running on, like you wind up the little wind-up toy and we're still running on the winding down, right?
Yeah.
Yeah.
Yeah. Do you think that there's any chance that we will ever know, and I don't mean in your or my lifetimes, that we will ever know why the universe started?
Yeah, I don't know that. I got an email about that the other day, actually. It was like, they were asking me a whole bunch of questions, and one of them was like, why is the universe here? And I'm like, this is not really my field. I think that's like...
But it's somebody's field.
I guess it's a philosophy question. Why do we exist? My field is how do we exist? How and when and where and all that. That's my field. Why is a tough question, because I feel like that implies some meaning or purpose or intentionality that I don't have access to.
Do you think there will ever be a time when we will know, like, how did the clock get wound up? Or how do universes actually start? Like, what's the sort of... Because, like, right now, most information we have about the universe comes in the form of electromagnetic radiation, whether that's visible light or whether it's, the cosmic microwave background. You can kind of like only see up to a point, and that's when light started happening, and that's where you get the data from.
Yeah.
There are, though, people who are thinking about, like there's this idea, and it's probably not real, but it would be an example of the thing I'm talking about, which is that like the universe is a black hole. And so like when a singularity forms, it forms a new universe. This is like a fun thought, and there have been physicists who have actually looked at it. She's shaking her head, everybody. I'm just using it as an example of there would be a precondition for the creation of our universe. Yeah, and then there's other people who are like, okay, so like the universe seems fine-tuned, and so you can infer the existence of something, of gravity, of like stuff. It seems like it has very specific conditions that would allow not just for like stuff, but for black holes or for planets or for life or something.
Right. Yeah.
And so maybe you can infer from that many universes existed or exist, and that this happens to be the one where this kind of stuff is possible.
Right.
And so like that's another way where you can kind of say a little bit of, well, we're inferring a little bit of information about how universes might be, and that there might not be just one of them, which is at least some data outside of this universe.
Right.
Maybe there is a someday that we will understand why universes happen.
I mean, we're certainly trying.
Okay.
So there are models that involve like cyclic universes where our universe comes out of the end of a previous cycle of the universe, and those models are a way of trying to explain where we come from. And people who work on these models look for sort of circumstantial evidence you might be able to find that would point you to that being the correct model. There are other models where, there's some kind of mathematical structure of the universe where the Big Bang was like a mirror and there was a different kind of mathematical version of the universe on the other side of that. And so like that would explain kind of why our universe was the way it was at the beginning. There's also models around cosmic inflation. So cosmic inflation is this process we think most of us think happened in the very early universe where there was a very rapid expansion, and then that rapid expansion slowed down to like a less rapid pace, and then there was the hot Big Bang that we think about, where the universe was very hot and dense. That happened after inflation. And there's a possibility that inflation just kind of keeps going, this idea of eternal inflation, where parts of this much larger universe kind of drop out of that inflationary state, have a hot Big Bang, and then become a normal universe, but that it keeps going in the background. And there's more of these universes kind of popping up. And that it's just always been going. Like that is one of the ways people talk about inflation. And we look for evidence for these things, but it's quite hard because like we can see the cosmic microwave background, but that's 380,000 years after whatever the beginning was. And we can't with visible light see, like with visible or microwave, we can't with any electromagnetic radiation see beyond that, because that's like a wall of fire from our perspective. It's like trying to use electromagnetism to see into the sun. You just can't do that because it's too, like it's bright, the light won't travel. So the people talk about using gravitational waves to probe that earlier time, and we've looked for evidence of gravitational waves from the inflationary period and so on, and we thought maybe we found them. Turned out we didn't, but we're still looking for that. And that might give us some clues about what started everything. But the fact that inflation you can't really see past inflation, because it would be something that would stretch out the whole universe so that parts of it are just completely outside of our horizon that we would never be able to have contact with. So there are certain limits on what we can know going into the past, and there are certain limits to what we can know going into the distance as well, because like we can't see beyond our cosmic horizon, which is defined by like, if the universe started 13.8 billion years ago, then anything where the light has to have taken longer than that to get to us, we can't see that ever. Right? There are certain limits. That's the only reason I'm not sure. Like I don't know if we're ever going to, if like there might be information that's just like hidden from us where we won't be able to figure this out. But I do think that by going through a bunch of these different models and seeing what kind of observational consequences we can find and trying to fit it together into a mathematical framework, we might get clues where we could at some point be pretty sure we understand that beginning.
I don't know did I hear you talking about this? There are these things that sometimes we could have known sooner. I'm trying to like get at how the process of science actually works, because there's a part of me that's like, we don't figure stuff out because we don't have good enough tools at first. This is definitely true. We're just waiting on the tools to get better, and then the tools get better and we find new stuff.
Sure.
But there's also a piece where it seems like we could have found stuff out sooner. We just had to wait for the idea to occur to someone or for someone to look at the thing through the right lens, or to like ignore what their advisor had told them or something.
I mean, that for sure happens. So I'm working on a new book now that's mostly about sort of particles and how fundamental particle physics builds the universe. It's called How to Build a Universe, theoretically speaking.
It's a very Katie Mack title.
So I'm kind of sticking with that theme. But one of the things that I talk about in that book, which is something that I learned about when I was writing the book, is so positrons, which are the antimatter version of the electron. Those were theorized before they were discovered, and they were theorized because basically somebody wrote down an equation about how electrons work, how they interact with things and move, and there was like an extra solution to the equation that didn't seem to make sense. seemed to have like negative energy, and they didn't know why that would happen. And it turned out that like if there's a positively charged version of an electron, then that equation would make sense, and that's what the positron turned out to be. So it was hypothesized based on this mathematical argument, and then later on, scientists who were looking at like tracks of particles in bubble chambers were able to identify like something that looks like an electron, but it's curving the wrong way in a magnetic field, indicating that the charge is the opposite. But there were tracks of positrons that were identified long before positrons were hypothesized, before they were talked about as a new particle. People just didn't really pay much attention to them because they didn't know what they were, right? Like there was just like, oh, there's a particle that's going that way. And so they were seen long before they were discovered. But because people didn't have the context for like, what could this be? It was just like, yeah, that's a weird little track in the plate.
Interesting.
It wasn't considered to be like, oh, I've discovered a new thing. That's an example of where like we saw something and it wasn't until we had the theory that we knew that it was actually an important part of physics, like antimatter, which is now a really big idea. It was the first discovery of antimatter.
Yeah, and nobody noticed it for a long time.
Yeah.
I mean, it just seems like we lived in a universe that made sense for a lot of time. I do actually feel like I still live in a universe that makes sense. It just makes a very different kind of sense. How do you feel about living in and being created by a universe that is so weird?
It's funny because so we are in a really interesting place in both cosmology and particle physics right now, in the sense that we have really good models for how everything works, and they all include stuff that we absolutely do not understand. So, for example, in cosmology, we have the concordance model of cosmology. It's called lambda CDM. That's the abbreviation we use for it. Lambda stands for dark energy, which is some mysterious stuff we don't understand that's making the universe expand faster. CDM stands for cold dark matter. That is this mysterious stuff that's holding galaxies together that we don't understand. And the whole model is named after those two things because those are the most important things in the universe. And we know that they're the most important things in the universe. We know how much of the universe they make up, and we don't know what they are. And that's an interesting place to be.
Yeah.
And then in particle physics, we have the standard model of particle physics, and it includes all of the particles that we've ever detected, all the ways they interact with each other. But the standard model does not include dark matter or dark energy.
Yeah.
And those things cannot be explained by that. And it's based on quantum mechanics and general relativity, it's based on quantum mechanics. General relativity is our theory of gravity that we're pretty sure works. It works really well, but it doesn't agree with quantum mechanics in certain ways. So something there doesn't fit. And so we have this whole thing where like we can do experiments that work every time, and all of our data agrees with the theory. All of our gravitational data agrees with general relativity. All our particle data agrees with standard model. And in cosmology, pretty much all of our cosmological data agrees with lambda CDM, although there are a few places where things are starting to look a little interesting. But it's full of these things that we don't understand how they work or what they're made of or how they fit together. And so it's kind of fascinating to be in that place where like operationally, like we know what the experiment's going to tell us most of the time.
We figured a huge amount of stuff out in terms of being able to model it.
Yeah, to being able to model it, being able to use it, like we use general relativity every time we use GPS, right? We use quantum mechanics in our phones and computers and all that. We can observe and catalog how much of what is, how much of everything is in the universe. But there are these huge questions around how it works and why it works, and we are still trying to figure that out. And I find that to be really, a really fascinating place to be.
To go back to like the process of science, do you feel like we're having a hard time figuring these things out because they're just very hard to figure out?
Yeah, I would say so.
Like they were just easier things to figure out at first, and we figured those ones out, and now we're left with the hardest problems.
Yeah, I think that we have to be more and more creative to find the places where the theories might not match the data. Like the way that you improve a theory is you take the theory as it is and you find the regime where it no longer works. and you get data from that, and it tells you how to change the theory. So if you're going from Newtonian gravity, a ball rolling down a hill, whatever, and you want to go to general relativity, which is Einstein's gravity, you have to work with like really strong gravitational fields, like around the sun and how Mercury processes as it moves around the sun, that kind of thing, or time dilation, which is a very hard thing to measure. So you have to have sort of the ability to make observations in that new regime. And so every time we want to improve a model, we have to find some contradiction with the previous model in the data.
Right.
And sometimes that involves moving to a new regime that we haven't tested before. Sometimes it involves just looking at data in different ways or finding weird little edge cases. But we're at a point where, like, technologically, it's very hard, maybe sometimes impossible, to reach those new regimes. And so it's hard to, like, improve the model by getting new data, because sometimes we can't get that new data. And then with stuff like dark matter, it's really hard to detect, right? And then dark energy, we're pretty sure it's out there, but like it's something that's throughout the whole universe, and it just makes the universe expand faster and doesn't do anything else. And so like, what do you do with that? Like, how do you explain that? I think like we have to be really creative in our experiments and our observations to try to find ways to poke at those edges, but also in our theories to try to find ways to reframe the theories or think about the theories differently such that it could allow us to develop the new theory that is better.
Oftentimes, the natural feeling is to feel like you're at the end of history, because you are, like, technically, like, the present is the end of the past.
Yeah.
But do you ever get the feeling that, like, we are still at the beginning of understanding the universe? Because I get that feeling all the time with being on the internet. I'm like, oh, we're babies at this.
It goes both ways. I feel like sometimes I'm in awe of how much we do understand. Like, we can see the beginning of the universe, right? Like, we can see the Big Bang directly, right, with our telescopes.
Yeah.
That's pretty impressive.
That's wild.
We can tell you what the stars are made of, right? Like, we can tell you what stars in other galaxies are made of. Like, that kind of stuff, it's really impressive.
Sometimes I think that, like, one of the things that we need to do more is to explain how, so that you understand that, like, when we're telling you things that really don't make sense and that we can't quite explain to you, we can explain to you, like, how we know how far away Alpha Centauri is, which is not something that you'd be able to figure out if you by just, like, sitting down and thinking. But then when explained, it's like, oh, you could actually get that.
Yeah. I love talking about that kind of thing, about how we know stuff, because I think it is useful for people to understand that, like, we're not just making stuff up, that there is a process.
Is that what you started doing, communication? Is that part of it? Why take the step and be like, I'm going to be Astro Katie on Twitter?
I think for me, it was just that, like, I get really excited about science and I just can't not talk about it. It wasn't really systematic at the beginning. It was just like, this is exciting to me. I want to tell people because it's exciting to me. Over time, I've tried to find ways of, like, being useful by explaining things. But mostly I just, like, I want to tell people because I want people to share my excitement. And in order to share that excitement, I have to tell people in a way that they understand, right? And so that has prompted me to try to be better at explaining things in ways that people will understand, so that they can have that moment of, like, oh, that's really cool. And, oh, I get that now. I never got that before. This is exciting. This is neat. Like when you go through the explanation of how orbits work and you see people's, like, eyes light up, like they'd never got that before, right?
Yeah.
That orbiting is just falling continuously and missing. Yeah. and you can get to that progression. You can say, like, if you throw a ball really hard in one direction, it'll go farther if you throw it faster before it hits the ground. And if you throw it fast enough, then it'll try to hit the ground, but the Earth will have curved below it and it'll just keep going. And it'll just orbit, And that's basically how this was explained when it was first discovered, how orbits work.
Very different from the idea that is sort of in your head immediately when you think of astronauts floating in space, which is that there's no gravity up there.
Right.
Which is not what's happening.
98% of the gravity that you have on the Earth, like, it's very similar gravity. They're just falling and missing.
In free fall all the time.
Yeah. They're just constantly falling. I've always wanted to know if, like, when you're an astronaut and you're sleeping in space, like, do you ever have that thing where you, like, wake up and think you're falling? Like, because you just are.
Well, I feel like you've met astronauts. Why haven't you asked?
I keep forgetting to bring it up, but, like, it's just, I don't know.
Does it happen more often, less often? What's it like?
And, like, do you panic? Like,
yeah. And then you're like, I am actually still falling.
Just never stops.
Oh, man. I want to ask you, so this communication work is I love it. I love the way that you do it. I love that you've decided to do it. Do you feel there's some amount of having watched other people do it and kind of wanting to take up that space in people's minds?
Yeah. Yeah. I mean, when I was a little kid, I picked up A Brief History of Time, right? Like many little kids who eventually get into physics, you pick up Brief History of Time. I think I was like 10 when I first read that, and I didn't understand a lot of it. Like there was a lot of it I didn't understand, but what I understood was that I wanted to understand it. I understood that like these are questions that I have that I want to ask. I want to learn how to ask these questions, and I want to, be able to like tell people about it. I think Stephen Hawking did a lot for cosmology as a popularizer in helping people to understand what those questions are and helping people to see the kind of awe and wonder about the universe. I think that like a lot of his writing was more elegant than it was approachable in certain ways. Like I think that like a lot of people have read A Brief History of Time and didn't understand it. I try to be understood. Like
it's an interesting balance. Like I'm a big Carl Sagan head and I love watching Cosmos, and there's times when I'm just like, all right, buddy. Reel it in.
But then there are other times you watch and there's something that's just explained so simply and elegantly and clearly, like when he talks about how they measured the radius of the Earth, and he just takes a piece of paper and bends it and shows how the shadow moves at different times. I mean, like that kind of thing is so well done. Yeah, Sagan was another person who I really looked up to when I was first thinking about doing science, but also like more locally. So I grew up in California, in Long Beach, California, close to LA, and there were earthquakes. And every time there was an earthquake, there was a scientist, a seismologist named Kate Hutton who would show up on the news. And she would tell everybody, like, it's not the big one. We can't predict earthquakes. And, like, just go through the science of how earthquakes work. And I really admired that she was able to, like, just be, like, the calm voice of reason and tell people stuff that they would understand. I liked to see that being done. I want to be the person who can, like, help people to understand a thing, right? It makes me happy to be able to do that.
It's wonderful and amazing that you get to do that while also still doing a lot of research, which you are also doing.
Yeah. No, I'm very lucky. I have a position at the Perimeter Institute that is explicitly split between the research and the outreach, and that makes me very happy.
Yeah, they give you time to write.
Yes. And I get a fancy title. My title here is the Hawking Chair in Cosmology and Science Communication.
That's pretty cool.
Which makes me very happy. Yeah.
Okay. Katie Mack, if there's anything that you've learned from doing this work that you wish everyone on Earth knew, what would that thing be?
So I think that the thing that I find kind of most awe-inspiring and delightful that I want to communicate, not because it's useful to anybody, but just because it's delightful, is how extremely insignificant and unimportant we are in the cosmos, and yet we can know stuff. Let me just give you some idea of how utterly insignificant and unimportant we are. Okay, I'm sure you've seen the pale blue dot picture from Voyager 1 in 1990. They pointed the spacecraft back at Earth. They were 6 billion kilometers away.
Out by Saturn.
Yeah, and there's an image of just like a little blue dot in a ray of light, and that's the Earth. And Carl Sagan wrote this beautiful story, this prose poem about that's us, that's humanity, and how small we are in this vast expanse of darkness. That picture makes me feel insignificant, right? Like, because that's like we are a tiny speck of dust. But in studying cosmology, it gets so much worse because the stuff we're made of is not important in the universe, right? Like humans are not important. The Earth is not important. We are not the center of the galaxy. The galaxy is one of maybe 2 trillion in our observable universe. And the galaxy is made of visible matter. And visible matter is only 15% of the matter in the universe. And the matter in the universe is only about 30-ish% of what the universe is.
The rest is energy.
The rest is dark energy, which we don't understand. It's something that is making the universe expand faster, but that's like almost 70% of what the universe is. And so we are so so incredibly insignificant, so incredibly insignificant, so incredibly powerless. Like, we have no control over any of this. The stuff we're made of barely impacts the evolution of the cosmos at all. But we can see the Big Bang. We can chart out the expansion of the universe. We can see other galaxies and understand their evolution. We can look at other stars and know what they're made of. We can hypothesize about how the universe is going to end and have reasonable ideas about how that works. We can understand the smallest components of matter and how they work and harness that energy, harness the physics of the interactions between particles on the quantum scale. And like, that is just so impressive that we can do all this as these incredibly insignificant little specks in a vast, uncaring universe. But we can understand, we can know, and that knowledge is the only power we have. And that is just incredible to me and wonderful, that the only sense we have any power at all is that we can understand and we can know and we can share that knowledge and we can work together to do things with that knowledge. That is what we can do in this universe. We cannot do anything else. And I love that for us.
You remind me of the cathedral again. So like, Artemis is very like a physical thing, that's doing a physical thing. But like the knowing is kind of one of the big cathedrals of the last, 100 to 500 years. There's just a lot of knowing that we've gotten. And of course, what is knowing for sure? Epistemologists might be mad at us, but we've gotten so much closer to reality. It's just like an amazing thing that we've built. Yeah. I just feel that curiosity is like wanting to know stuff. It's like maybe like second best human tendencies.
This is just part of human nature that we want to understand and share that understanding. Like, we want to know stuff and tell people about it. That's like one of the biggest drives we have in life. You talked about like life wanting to multiply itself and stuff like that. And that is a thing that is part of human nature. But like, also there are people who are living with 5 roommates on ramen because they just want to know, right? and that is what they devote their lives to, is just building an understanding of the cosmos to share and to build on for future generations. That's a very hopeful thing as well, I think. One of the things I loved about Artemis and that I love about space exploration is it is an expression of hope about the future. A society that has no hope about the future doesn't do a moon mission, right? Yeah. Like, you don't go out and explore the cosmos if you don't think that some future generations are going to learn more, use that knowledge, or build something bigger. Like, that is an expression of hope and optimism, and I love seeing that happen.
Yeah. Thanks to all the humans who helped make this episode. Morgan Levy is the show's supervising producer, and Greg Rippin is our engineer. Peyton Mitchell manages our social media, Andrew Huang composed the music, and James Barnard designed the artwork. You can, and should, follow us wherever you listen to podcasts.
Let's do it one more time.
Humans.